Hi friends, this class will be based on a Clapetron method of moment distribution. In our previous classes, we've talked about the Hardy-Cross method of moment distribution and the slope and deflection method of moment distribution, of which I used the same example. I solved same example with both methods and got same answer, and here I'm going to use the third method, which is the Clapetron method of moment distribution, or you call it the equation of a three-moment method, to use and solve that same example, and as well know if to give me the same answer. Right now we are going to throw a little bit light into Clapetron's method of moment distribution. Here we get to know that this method is exact and may be cumbersome when the number of unknowns exceeds 3. It consists of obtaining a set of simultaneous equations which are solved to obtain the support moment. The equation as stated by Clapetron is given below. We have m sub a L sub 1 all over E sub 1 L sub 1, where m sub a is moment at point joint A, L is the length of joint A to the nose joint, and E is the modulus of elasticity, while I is the moment of inertia. Then plus 2 m sub b in bracket of L sub 1 all over E sub 1 I sub 1 plus L sub 2 all over E sub 2 I sub 2 bracket close plus m sub c L sub 2 all over E sub 2 I sub 2 plus 6 times a sub 1 and x bar sub 1 all over E sub 1 I sub 1 L sub 1 plus e times a sub 2 x bar times x bar sub 2 all over E sub 2 I sub 2 L sub 2 is equal to 6 h sub 1 all over L sub 1 plus his h sub 2 all over L sub 2. From here you can see I listed what each of these symbols stand for. You can take your time, read them up, and digest it into your system. Of course, the system I mean here is your brain. So special cases of three-moment equation. If all the supports remain at the same level, then h1 and h2 are 0, and the equation will be equated to the 0. This is it here. That's when this and this becomes 0. There is no sinking of support on the structure you're dealing with. Then the equation automatically changes to this. Then the second special case is if the flexural rigidity of all the span is same, that is the E sub I sub 1 I sub 1 is equal to E sub 2 I sub 2 is equal to EI, and the supports are at the same level, then the equation becomes this. So at that point you know that the E and Y multiplied by 1 is 0. That's when all the span is same. You end up having this equation. Now when the end of the structure is fixed, the theory of three moments can be modified by imagining a span LO, just as I did in Hardy-Cross method, and as well as slope and deflection, and moments of inertia LIO, and modulus of elasticity beyond the support, and applying the theorem of three moments. So this is it here. We end up having this type of equation if you have a fixed end at one of the joints of the structure. You have to do this. So having known all the necessary conditions, let's take an example and look through it. Determine the support moment of the beam shown below. This is exactly the beam I used in the example I used in Hardy-Cross method and a slope and deflection method. I didn't remove anything, I didn't add anything. So step 1, using Clapetron's method of a three moment. Step 1, write down the three moment equation necessary for the question at hand. So you can see I wrote it down. There is no sinking of support. Therefore, H1 and H2 become 0. Then the flexural rigidity EI is constant in all span. So I put that 1. Is same in all span. I put that 1. We end up having this equation. So step 2, take note of any special case. Since the support A is fixed, a span LO is assumed at that point and applied the 3-moment equation. Step 3, consider 2 spans at a time and generate the required support moment equation. Considering span A prime AB, obtain A prime AB. Obtain the free span moments of each span, the area and centroidal distance of each shape. For span A prime A, you have AO, A sub O is equal to 0, L sub O is equal to 0, and X bar sub O is equal to 0, reason no loading on the infinite beam. For span AB, A sub 1 is equal to 2 over 3 times base times height, where B is the base, Y is the length, the span of that beam. Then X bar, which is the centroidal distance, is equal to L over 2 for this particular shape, as I stated earlier. Then that's 6 over 2, that is equal to 3 meters. And H free span moment is equal to WL squared over 8. That's because we have a UTL at this span. Then we have 270 kilonewton per meter. So therefore your A will be substituting this and what we have here. You get the area of the shape in meters squared. Now substitute the above into the equation of span A prime AB. You end up having this. We generated this equation for us. Now you consider span ABC. That's this span ABC. If you consider that, you generate this equation. Then height MC is equal to 0, simply supported. Therefore, it automatically becomes 0. A prime, we already got that. Sorry, A sub 1, we already got that to be this. X bar sub 2, we already got that in the length. Then for A sub 2, that's for the UDL load, that's 25 kilonewton meter. You have 2 over 3 times 5.5 times H, where H is WL squared over 8. You have this substitute there, you get the area. Then the X bar 2, that's the centroidal distance of that shape, sinusoid is, and the length is 5.5. Now we go for the point load. You get half base times height, which is the area of the triangle, and the height for a point load, as the maximum span moment for a point load, is WAP over L, as I stated earlier in the special cases of moment distribution. So you have this, put the values here, you get this as a H. Therefore, the A sub 2 point load is equal to half times 5.5 times 127.27, get 350 meters squared. Now, for the centroidal distance of this shape, you have L plus B over 3, the 5.5 plus 3 points, where the length is still 5.5. Substitute the above into the equation of 3 moments that we generated. You end up getting this, which is equation 2. Now step 4, solve the equations generated simultaneously. Once take this equation and this equation and solve it simultaneously, you have that MA is equal to 174.87, the same thing as the other method gave to us, and MB is 190.265. You can see the exactness we talked about. Like in slope and deflection, we got 263, but here we got 265, which is better. It's more exact than that. Then draw the bending moment and draw the support bending moment diagram. This is it, as we have always done. Now, getting the shear force, I think you use the same method as I've shown you in a Hardy-Cross method of a moment distribution. Use that method to get your shears at this point, and this point. Thank you very much for watching this video. I hope to see you in our next class. Goodbye.